All right, let's go and get started. I'm going to go ahead and get the sign-in sheet passed around. I'm remembering it today. Here's that. Okay, so a couple announcements. Number one, homework 4 on bolted connections. I'm assigning that today. If we don't finish bolted connections today, we'll be damn close to finishing it between now and Friday. So I'm assigning that today, and it's due next Wednesday, so there's a week on that. It's not a particularly complex assignment. I will admit, because of the bolt bearing cases, it can feel a little bit like busy work, and it sort of is what it is with bolted connections. But I'm assigning that today, and it's due March 1st. You can probably attack most of it right now. And as for the slip critical stuff, we're going to do that today. One thing I will point out, so Engineering Career Day is hosting a social, or SAME is hosting a social for Engineering Career Day, which is tomorrow. They're hosting it at Roosters starting tonight at 5 p.m. It's hosted by the Huntington Post. Great networking opportunity. I think they love it when students are there, because if it's just a bunch of professionals, it sort of defeats the purpose of the event in general. So if you're interested, go ahead and show up. I think the food's on them. Drinks aren't, but food is. So, what's that? Wow. But that's a choice. So yeah. Hold on. I'm curious. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. All right. Just curious about something. I was curious how many people were here. We have quite a few that aren't. Is it rainy? Is that what it is? Because it's rainy, it's cold and gray. What's that? Oh. I know everybody is they're having to settle on the fact they've got a soils exam. No, I know you have one today.
You and Huffman hang out too much because he's starting to force jokes like you do.
Force jokes?
Yes.
Well, I mean, they have to be natural, otherwise the jokes don't have much cohesion, All right. Does everybody have a copy of the homework? If you want to do 7 homework assignments, you're more than welcome to. Do you all delegate the homework production to him? Man, you're getting voted out. I'm just saying. All right. So there's 3 problems. One thing I will point out, we're going to do a slip critical design today, but we are not going to lay out the connection or analyze bolt bearing, because we've already done that. Okay, I'm not going to do the same thing like 3 times. So we're literally just going to do this slip critical design example very quickly, and then we'll sort of move on from it. But let me go back to the notes, because there's a couple things I want to sort of review before I at least pull up the homework assignment and get everybody acclimated back to what we were talking about. So first thing, I'm going to hop back and forth a little bit, but I just want to sort of bring it back to the topic at hand. So we're talking about the slip critical capacity of bolts. We discussed that our nominal capacity is computed as follows. We have essentially our coefficient of static friction multiplied by our normal force. In this case, our coefficient of static friction is mu, and our normal force is T sub B. And we take those 2 quantities, multiply them together, but then we adjust them by a number of different factors. D sub U is our multiplier to account for the difference between the pretension that we're specifying versus the pretension we actually get in the field. And the facts are we get way more in the field, so much more that we can actually up our design capacity by about 13%. H sub F is our filler plate factor, and in most cases, especially, and essentially all cases we're going to do in this class, we're just going to take h sub f to equal 1, and n sub s is the number of slip planes. Now, a couple things. So phi is 1, but one thing I'll point out, a lot of this stuff I want you to understand, but you really don't need to employ, because if you skip ahead a little bit and you go to the manual, and I think we looked at this last time, there's a nice, easy-to-use design guide in the manual that's right after the bolt shear table. So if you've got that tab near the bolt shear table, it's literally right there. So I'm not telling you to tab this twice, because it's literally, it's right there. Okay? Now, a couple things. Let's be clear on the design procedure for bolted connections in general. Like I said, I am hopping back and forth a little bit, but I want everybody, going the wrong way. Go right here. Okay. I want to be clear on the bolted connection design procedure. So what do we do? So we start off, we have a factored load. We determine the capacity of a bolt, divide to obtain the number of bolts, and that's it. For bearing type connections, all we care about is the shear capacity of a bolt. But when we look at slip critical connections, we care about the shear capacity and the slip capacity of the bolt, and we just take the smaller one. In other words, we're saying, which capacity is going to govern the design, and it'll be the smaller one, either the shear capacity or the slip capacity. Now, what we are not going to do today, but what I want you to be equipped and able to do is, number one, lay out the connection according to prescribed requirements. So make sure that you can follow this. You're going to space based off of preferred spacing and minimum edge distances. And make sure that you can calculate bolt bearing capacity, because you still need to do that. You can't do that at the onset because you have no idea what the connection looks like. Okay? Sound reasonable? All right, anybody have any questions? All right, so what we're going to do is example 10, where we're going to determine the number of bolts in a slip critical connection. And this is going to be a very quick example. So I'm on slide 197. So we're going to design this connection as slip critical. So we have group B bolts. Now, if I just pop quiz, if I didn't tell you that the threads were included or the threads were excluded, what would you assume? Included, worst case scenario. So group B bolts with the threads included, 3/4 inch diameter. We have A572 grade 50 steel. Now, to be honest, the A572 grade 50 steel really doesn't matter for determining the number of bolts. The only time that matters is when you're going back and checking bolt bearing. Okay? Sound good? All right, so this, like I said, this is going to be a really quick example. And we'll just list what we need to do afterwards, because again, I don't want to sort of do the same thing over and over again. Okay. Yes. No, that's a good question. No. And the same thing's true on the homework. Okay, if you look at the homework, read what it says on problem 1. It says, for the purposes of this problem, do not check gross section yielding, do not check neck section fracture, do not check block shear rupture, do not check slenderness. Would you have to do it in real life? Yeah, but we've already done that. We don't need to do it again. But my primary concern is, do you know how? Which I already assessed that during our first celebration. So, sound good? Anybody else? All right. Okay, so let's look at example 10. All right, so... All right, so first off, what do you think the first thing we ought to do for example 10 is? Factor the loads. So we have a dead load of what, 65 kips, and a live load of what? 115. So factored load. All right, so PU is 1.2 P dead plus 1.6 P live, 1.2 times 65 plus 1.6 times 115. And plug and chug, that comes out to be what? 262. Do I got a second on that? All right. Okay. So that's the factored load. Now let's take, since this is a slip critical connection, we are going to need, we need to assess the shear capacity of a bolt and then the slip capacity of a bolt. So let's start off with bolt shear. Okay. So bolt shear. And we are in table 7-1. Okay. So let's start recalling a few facts that we're going to need to look up the capacity of one of these bolts. So first off, let's see, what's the diameter of these bolts? 3/4. So we've got a 3/4 inch diameter bolt. Okay, it's group B, and I told you it was threads included, but if you didn't know, you would assume group B in. Now help me out. Are we in a situation of single shear or are we in a situation of double shear? Single. There we go. All right, single shear. All right, so now based on these quantities, what is phi RN? Remember, I draw that little n to say it's phi RN of a bolt. 22.5. All right, sound good? Okay, now literally just do this. Take this and turn the page. Okay? All right, so we're on bolt slip now. Because we are designing a slip critical connection, we have to worry not only about the shear capacity of the bolt, but also the slip capacity. So let's look at slip, bolt slip. So this is table 7-3. Okay? Now, let's look at a couple things. One of the things about this table is the fang surface. What class fang surface is it assuming? A, so a mu value of 0.3. Okay? Now we have class A fang surfaces with a mu value of 0.3 or class B with a mu value of 0.5. Now if you don't know, let's just think about this. What would be the most conservative to assume, a class A or a class B? Class A, because that's going to be a lower coefficient of static friction, and that's going to yield a lower capacity. Okay? Sound reasonable? All right, so right off the bat, the fact that we are using this table says we are making an assumption of a class A fang surface. The problem didn't say that, so when in doubt, assume class A. Now, if you look at the bottom, I mean, if you look at these little notes here on the bottom, it says, and you can even read it, it says for class B fang surfaces, just multiply whatever you get in the table by 1.67. So you can use this table for class B as well. Okay, so let's write down a couple things. So first off, which table are we going to look at? Are we going to look at the page on the left or the page on the right? The right, because the right is for group B bolts. So right there, I guess I ought to mention group B. Now, it doesn't really matter whether or not threads are included or excluded from the shear plane, because we're not talking about bolt shear, we're talking about bolt slip, so it doesn't really matter. We have, again, a 3/4 inch diameter bolt, and we're talking about single slip, so a single plane. So based on these parameters, what is phi RN? Now, if you look on the table, it says, you know, standard hole, oversized hole, slotted hole. We're dealing with standard hole. 11.9. Everybody see that? Okay. Now, so let me ask you this. If I am designing this connection, I'm going to take the load and divide it by the capacity of one bolt. Should I divide by the shear capacity of one bolt or the slip capacity of a bolt? Slip capacity. Slip capacity is going to govern the design because in bolt shear, the bolts can hold up more load. So if I'm trying to determine the number of bolts, I'm going to determine based off the worst case scenario, which in this case is this one. So I'll say this governs. So therefore, the number of bolts what do we have? We have the number of bolts is PU over phi RN, which is, what, 262 divided by 11.9 kips per bolt, which is what? Somebody do that division. That's 0.9, not 0.7. Let's just do the decimal. 22.02. All right. Now, let's ask this. Should we round to 23? It's a weird number. So how about 24? Use 24 bolts. Now, that might seem like a lot, and it is. One of the things about slip critical connections, so let me say this. So one of the things about slip critical connections is when you have a slip critical connection, a rule of thumb is you're probably going to be using about twice as many bolts as you would in a regular bearing type connection. And that should make sense if you look at the numbers. I mean, the bolt shear capacity was what, 22.5? The bolt slip capacity is 11.9. Now, I'm sure that there's some of you are thinking, well, do we need to check bolt shear? Yes, you need to check bolt shear because we don't live in a world of alwayses and nevers, so you do want to make sure that you're at least making sure that bolt shear doesn't govern. All right. Sound good? Yes. But, okay, well, what if it was, I do see what you're saying, that it's pretty close, but what if it was 22.4? Would you round down to 22 volts? Okay, all right, so you are agreeing that the conservative approach would be to round up, not round down, okay? What I'm saying is, when I say, first off, when I see 22 point something volts, I'm always going to round up. I mean, let's be clear. When you're designing connections, connections are the one area where I'm going to say, when in doubt, be conservative. Okay? You look at the history of structural failures that have happened, throughout history, and you will find that more often than not, it's not the main members that fail, it's the connections. So I sort of take an attitude where I don't play around. If it says 20 point, no, I'm going to round up. Okay? And I'm going to say 24 because, take Hyatt Regency. The members didn't fail. It was the connection that failed. Okay? So I see what you're saying, but no, I'm rounding up. Yeah. Now let me say this. I'm not saying take it, let's use 40 volts. I'm not saying that. I'm saying I'm not going to leave myself open to that. I mean, you got to think of it like this. If a main member fails, that's just one member. If a connection fails, that's multiple members. I mean, what is a connection? Taking multiple members and putting them together. So I'm not going to play around with that. Is that a fair answer? All right. Everybody else okay with that? Now, let's continue this problem at least in our heads. Okay, what would be the next step after this? I got 24 bolts. Is the connection designed? No. Why? What's left? We have to lay it out. So we have to do spacing requirements. We have to do edge distance requirements. Then what would we have to do? Check bolt bearing. Okay. Now, if we really wanted to continue this problem further, we've got to check gross section yielding. We've got to check next section fracture. We've got to check block shear rupture. We've got to check slenderness. We've got to check all that. All that stuff still matters. Okay. Does that make sense? All right. If that makes sense, I do want to at least pull something up on the homework assignment to kind of enhance some clarity of some things. So here's the homework assignment. let me at least pull up problem 1 to kind of explain what's going on here with problem 1. So with problem 1, you need to determine the capacity of the connection. Now, a couple things to make your life a little easier. So number 1, if you look, like let's take a look at one of these splice plates. So one of these splice plates has, what, 16 volts? Like that's one splice plate. But when I'm looking at the connection and I'm trying to analyze it, I wouldn't consider that that splice plate has 16 volts. I would only consider 8. Okay? The easiest way to go about performing this type of analysis is break out the old samurai sword or lightsaber, cut a section literally right through here, and then what you've got is on top you have a plate going like this, and down here you have a member, you know, going like that. And then you also have this as well. Remember I said that when you do a bolted connection analysis, you always have 2 cases of bolt bearing? Well, that is definitely the case here. Because if you look, I've got a W16 by 77 that's transmitting load this way, and then I've got 2 splice plates that are transmitting load this way. Okay? So if you think, remember when we did bolt bearing's a function of your layout, and then your thickness, and then your steel, right? So if I look at the splice plates, I've got 3/4 inch and 3/4 inch of A36 steel going this way. But on the I-beam, I've got a W shape, a W16 by 77, so the thickness is going to be whatever the thickness of that flange is, and it's also A992 steel. So you just got to check both. Okay? So you're going to have 2 cases of bolt bearing with this one. Okay? Does that make sense? Did that make sense on that last example that we did where we had to go through and check the bolt bearing on both cases? Everybody remember that? Does everybody remember? I mean, I don't see many people shaking their head. Hold on. I'm talking about this. Remember when we looked up the shear capacity of a bolt, and then we had the bolt bearing, we had the center plate, so we looked up these dimensions right here, and then based on the spacing, the edge distance, and the thickness, we then said, all right, we can go through and calculate our clear distances, calculate our edge capacity and an interior capacity, and then go through and compute VRN. But that was just one case of bolt bearing. We needed to go through and do it again because we had the cover plates. And remember I said let's just use 2 times the thickness and then edge distance and spacing and go to work. Does that make sense? Everybody okay with that? So I'm trying to go through this now because I've given similar problems to this before, and what I end up finding is that the students aren't checking enough cases, or they're literally just verbatim doing exactly what we did in class and then stopping. And the problem is, like, I did this one in class, I analyzed it, but I didn't do it on example 9, and I didn't do it on example 10 because it's literally the same procedure. Okay, so does that make sense? Everybody all right on that? Okay. Now that's problem 1. Problem 2 is a connection design. Oh. Okay, problem 2 is a connection design, but a couple things about this. So number 1, this is a slip critical connection, so you've got to check bolt shear and bolt slip just like we did this time to design the connection. As for laying, you also have to lay it out. As for laying out the connection, I want you to use 2 lines of bolts. So for instance, if the answer is 8 bolts, so you're going to have something like 1, 2, 3, 4, 1, 2, 3, 4, like 2 lines of bolts. Okay? Now you can use spacing and edge distance requirements to lay the bolts out in this fashion. As for laying them out this way, use table 17A on page 1-48, and there's a nice little gauge spacing table on the bottom of the sheet. As for bolt bearing, you actually really only need to check 1 case of bolt bearing, because if you look, you have 2 angles that are 1 inch thick, but you have a plate in the middle that's only 3/4. So which one do you think matters? The 3/4, the one in the middle. Okay, make sense? And it's all the same steel, so it's an easy pick. All right? Sound good? Now, the only one that you haven't done yet is, which is what we're going to talk about now, is this one. Okay, and this is a little different. Okay, this is unique. This is a combined loading problem, and that takes a little bit of discussion. Okay, is everybody good so far? Anybody got any questions? Yes, I do. All right. Okay, now, then let's talk a little bit about bolts in tension, and let's talk about combined loading. So let me explain what I mean when I'm saying bolts in tension and what I mean by combined loading, because this is kind of important. We'll borrow this real quick. So what we've been talking about up until now are bolts in shear, and what I mean by that is here's a bolt, here's me, and I'm shearing it. Okay, I'm taking the load and I'm applying it like this. Okay, now that's bolts in shear. Bolts in tension is I'm taking the bolt and I'm literally yanking on it. Okay, the reason why we've got to discuss bolts in tension is what if you have this? Okay, this scenario is a little different because if you look, I mean, go back to basic statics, I can take this load and split it up into X and Y components, right? So I've got some load that's going, what, like that? So it's yanking on the bolts in tension, and then I've got a vertical component that's going like this, and it's loading the bolts in shear. So what I have is a situation where the bolts are experiencing both shear and tension, okay? And this is called a combined loading problem, and combined loading problems are a little unique in the world of structural engineering. They happen in a number of different cases. They happen in steel design, they happen in concrete design, and we're going to talk about different instances of them throughout the semester. But in order to discuss combined loading, we have to discuss each individual component. So the idea is if you have a section that's in combined loading, let's say you have a bolt that's in shear and in tension, you have three checks. Check the bolts in shear, check the bolts in tension, and then check the interaction between the two. So we got to handle each one at a time. Now, bolts in shear, I think we've talked about that until we're blue in the face. I think we've covered that pretty well. I mean, we've got bolt shear, we've got bolt bearing, we've even got bolt slip. Okay, so we got that. Let's talk about bolts in tension. Now, if we were talking about a pure connection that has a bolt in tension, we're probably talking about something like this. So if you've got some sort of hanger-type connection, let's say you got a W-beam, you got a WT, and you're got a load hanging off of it, those bolts connecting that hanger to the I-beam or to the wide flange, they'd be experiencing pure tension, am I right? So the design of bolts in tension is pretty simple because, first off, the bolt in tension and a threaded rod are designed essentially in the same fashion. First off, the equation is exactly the same, okay? That's number one. Number two, the actual conceptual aspects of a bolt in tension get a lot simpler. I missed something? Or I thought there was a joke. I like to be included in the joke sometimes. Everybody's smiling. What's up? Happy to be here. Okay, all right. When we talk about bolts in tension, there's a couple things that make our life a little easier. So number one, it doesn't really matter whether or not the threads are included in the shear plane, because there is no shear plane. We're not talking about shear, we're talking about tension, so it doesn't matter. Okay, so that's point one. It also doesn't matter how many shear planes there are. It doesn't matter if there's single shear, double shear, triple shear. There's no shear, it's just tension. So literally nominal stress times an area, there you go. Okay. We also don't need to even do much math because look at the table right next to 7-1. Look at table 7-2. It's literally right there, the available tensile strength of a bolt. Diameter, group, there you go. It's incredibly simple, okay? Good? All right, so looking that up is pretty easy. What is an issue is if you've got combined loading. So first off, does everybody agree that we've got two stresses on those bolts? We got shear stress and we got tension stress. Everybody okay with that? All right, so if you've got both, we handle the bolt capacity and shear, we handle the bolt capacity and tension, and then we handle the interaction. Now, interaction is a unique concept. The idea is this. If I have a bolt that's experiencing something like that, I'm going to borrow this again, something like that, that diagonal loading, okay, it really wouldn't make sense. I'm going to try and state this as clearly as I can, but let's look at it like this. If I'm loading it in shear, I would expect that I can load it in shear until I reach 100% of its shear capacity, and then it's going to fail. Sound reasonable? If I load it in tension, I can expect I can load it until I reach 100% of its tensile capacity. Sound good? But if I got shear and tension going on at the same time, it really wouldn't be reasonable to expect that if I got both of them going on simultaneously, I couldn't reach 100% of the shear capacity and 100% of the tensile capacity. The fact that you've got two loads going on at the same time would serve to weaken it a little bit. Maybe if you've got shear and tension, maybe I can only reach about 70% of the tensile stress and 70% of the shear stress or something like that. Does that idea kind of make sense? The fact that you've got multiple things going on, you can't quite reach 100% of each component. You know, the presence of one is going to reduce the capacity of another. That kind of makes sense? Everybody okay with that? So, first off, if you go down to the lab and do some tests on a bunch of bolts, you'll find that the behavior really closely represents the following elliptical relationship. So if you go down to the lab, what you find is, so like for instance, if I've got the bolts loaded up to about, let's say 50% of their shear capacity, I can only expect about, I don't know, maybe 80% of their tensile capacity. Does that idea kind of make sense? And if I got more shear stress, like all the way over here, well, that tensile capacity drops even further. Sound good? Now, the problem with that relationship is the equation of an ellipsis requires a lot of math. And engineers don't like math. They like to keep things simple, am I right? You're like, engineers don't like math. Why did I get into this field, right? In all seriousness, if you go down to the lab, this is the model that's used, or the model that you'll find. But the model that's used is this sort of trilinear fit that you see plotted on top. So like this linear fit here, and then this line, and then going down. So let me explain sort of what this means. So first off, if you notice the fit that you see this 0.3. So you see 0.3 on the tensile stress and 0.3 on the shear stress. Everybody see that? What that means is that it's the code's way of saying, you know, you only need to do an interaction check if the relationship between the amount of shear and the amount of tension is has enough impacts. So here's an easy way of saying it. If I got a connection that's got 100 kips of shear and 2 kips of tension, do I really need to worry about interaction? You think 100 kips in shear and only 2 kips in tension. No, right? There's tension, yeah, but I don't really need to worry about that interaction because the relationship between the amount of shear and the amount of tension is so small that it's not that big of a deal. What the code is saying is that if you take that shear and that tension and they get within 30% of one another, then you got to start worrying about it. So in other words, if I got 100 kips in shear and then like 40 kips in tension, now those loads are going to start to have more impact on one another, and now we got to start to assess it. That make sense? So once we hit that 30% threshold, that's the code's way of saying, all right, 30%, okay, now we need to start worrying about interaction. So if you got a ratio less than 30%, don't worry about it. If you do have that significant relationship, you know, like 180 or 170, and you do have that relationship, you have a nice little linear equation of a line. And that equation is specifically as follows. So what we do is we compute a nominal capacity, and the way that we do that is we say, all right, a nominal capacity for a bolt is just a stress times an area. Well, the stress that we compute using this equation down here. Now, if you take a look at this equation, I know it looks kind of funky, but let's take a look at it. We have 1.3 times the tensile stress minus this pile of junk times shear. Now, if you take a look at this and think about it, this is essentially the equation of a line, and it's y equals mx plus b. Let's talk about b. B is the y-intercept, right? And I propose the y-intercept is this value right here, the 1.3 times the nominal tensile stress. think here's my line. What happens if I took that line and sort of started to track it up all the way up here? What would I hit? Well, if this is 0 and this is 1, maybe this up here is, I don't know, 1.3? That makes sense? Okay. Now y equals mx plus b. X is what's going on this axis, and that's the shear stress, right? Well, there's x, right? So this term right here, this FNT over phi FNV, that's the slope. And it's negative, which means the line's going down. Make sense? All right. Sound good? Now, FRV is the applied shear stress, which is, I'll talk about that here. If you go to the code and you open up Chapter J and look at the equation, you'll see a user note below the equation for FNT prime, and it says, note that when the required stress, either in shear or tension, is less than or equal to 30% of the corresponding available stress, the effects of interaction or combined stress don't need to be investigated. So this is the code's way of saying if one value is so significantly larger than the other, don't worry about the interacted effect. Okay? Now, another thing, if you look at the equation, it's another one of those, the capacity equals a pile of junk such that it's less than or equal to another pile of junk. So that's where we're going off the minimum. Yes, sir. It's accurate enough. I was really being a little facetious there, but it's just, this is close enough. I know. I was being facetious when I said that. I was just being silly. This is close enough for government work. So, all right. My goodness. All right. Okay, this slide right here, it doesn't have a lot on it, but it's really important, okay? And I really want this to be very clear, okay? Let's look at the capacity again, okay? The capacity, what does it say? It says the nominal capacity is FNT prime times AB, okay? So what we are doing is we are computing a modified tensile capacity, okay? Modified tensile capacity. When we calculate phi RN, we compare it to the tensile load, okay? So what that means is, if I go to this, okay, let's look at this example. So I'm going to factor this load, right, and I'm going to get a PU, right? So I'm going to get a PU, I'm going to split it up into the X and Y component. The X component is going to be the component that's in tension, right? I compute this phi RN right here, and I compare it to the tension component, okay? And that's important because I guarantee there's going to be a couple folks in here that mix that up, all right? So that's something you want to start just sort of keep in the back of your head. Yes, sir?
When we're looking at the tension capacity, do we consider the preloaded bolt, say if we're doing slip critical connections?
That's a good question. So the question was, if you've got a slip critical scenario, do you need to consider preloaded? Two answers. Number one, yes, but not in the way you're talking about. If you go to Chapter J, in fact, let's everybody take a look at this. I want to go to this. So let's go to this. So 16.1-125. Okay. Okay. I heard something. All right. So I'm on 16.1-125. Does everybody see that, the equation that we're talking about right here? Okay, so this is where this particular equation is in the code. So your question was, do we need to consider that additional effect for slip critical? The answer is yes, but not in the way you're talking about. If you turn the page to 16.1-127 and you look at item number 9, see where it says combined tension and shear and slip critical connections? You essentially compute the modified tensile capacity, but there's an adjustment factor that you incorporate to account for that preloaded tension that you're talking about. So the answer is yes, but it's sort of incorporated on the capacity side, not the load side. Does that make sense? That's a really good question, though, the fact that there's already tension in the bolt, so do we need to consider that? And yeah. I'm not going to do that for you to you on an exam, though. I'm really just interested in you understanding interaction in general. All right, that's a good question. Anybody else? This is good stuff. let's see if we can at least get this next example started. We'll try and knock some of it out, and we will probably finish it on Friday. But so here's the example. We're going to analyze this connection. I'm just going to go ahead and be absolutely frank. The W14 by 90 and the WT 10.5 by 31, they really don't matter. I'm not interested in really checking bolt bearing for this problem. I'm really only interested in the group of bolts. Now, I am curious, how many bolts do you think are in this connection? 4. This is a WT, right? So this is the flange, right? And this is the web sticking out of it, right? So there's 2 bolts on this side, and then there's going to be 2 bolts on the other side. So there's a total of 4 bolts. Does that sound good? Now we're also on a 3 to 4 slope ratio, so this PU, we can split that up into X and Y components. Yes, sir? That is true. You're right. It could be 8. Well, it's a WT 10.5 by 31, so I don't know that we could fit 86. Well, 86 isn't divisible by. Yeah, it is. 14. Yeah. What's that? They're not 2-foot diameter bolts. I actually have that listed though. We should. All right. Is everybody good on this? Okay. Okay, so this is example 11. Okay, so first off, let's see if we can, let's start off by factoring the load. Let's just go ahead and do that. So PU 1.2 P dead plus 1.6 P live 1.2 times, what's the dead load? Plus 1.6 times, what does that come out to be? 90. Okay. Now, as for the tension and shear components, all right, let's make sure we're clear on what's going on. So I've got a column, I've got a bracket, and I have a load going through that bracket and that series of bolts that looks something about like this, and you're telling me that's 90 kips, right? Okay, and my bolts are sort of like that and like that. Okay, now, help me out. This was, let's see, this one was 3 and that one was 4. Is that right? Okay. So let's take a look at this. So I propose that what we need to do is this. We have a factored load, right? Now that load is on an incline. So what we need to find is the factored tension component and the factored shear component. Sound good? So help me out. All right, let's split this up into X and Y. So the X component I propose is 4/5 of 90, and the Y component is 3/5 of 90. Sound good? The X component, the 4/5, is that tension or shear? Tension. There we go. So I propose 4/5 of PU is our tension component. And then this is 3/5. All right. So what do we have for these? Second on that? Okay, all right. Now, let me also be clear, okay? This right here is the tension and shear on the connection, okay? And this is where bookkeeping really becomes important, all right? I'm also going to compute this, TU per bolt. So TU over the number of bolts. So 72 kips over 4 bolts is 18 kip per bolt. And I'm going to do the same thing for shear. And what is that? $13.5. Okay. All right. Sound good? All right. Yes. You could. You just take the shear component and then, but you need the dimensions. I mean, we don't have the dimensions. So. That's a good question. It depends. Or let me answer that two ways. Number one, it just depends on the comparison between the load and the resistance. I mean, it's not as simple to say, oh, this will always happen, because it depends. You know, it depends on the magnitude, the dimensions, all of that. I will say that when you have elements in tension, there is an effect called prying action where you can have a T shape. Like, let's say you got let's keep it simple. Let's say you got an angle and you've got, a plate right here and you've got a bolt sticking through it and you load. What can happen is you can actually start to fail the angle, and it kind of does like that whole thing. I'm not a good artist, but you see what I mean? The angle is sort of bending, or sort of failing and bending. And that effect is called prying action. It's a really plug and check, and we might talk about it later, but right now I just want to focus on the interaction. So, because that's going to become important for other topics later, like beams and columns and stuff like that later. Sound good? Any other quick questions? All right. One final point before we leave, and I don't want to get too unpleasant, but do me a favor and try and start showing up on time. It was like 1 minute before class, and we had like 8 people here. Now, we had a rush coming in right at 9, which I'm not too worried about, but do try and be on time. So that's all I got. We'll see you.